I've talked about with Bill in the past is E4th, and we've put that up on this chip. We talked about it a couple of years ago. And at the time, I was really embarrassed because the only thing I could show it running on was an FPGA model of the chip. Now, since then, we've made a few changes and gotten it running here. Now, what is my... There, okay, good. I may, let's see. Oh, I'll just use this. I won't use the whiteboard. For the tape, I'm John Rible, contractor working with Intellisys for a really long time, too. And I'm probably going to move around a little bit, Dave. So, yeah, good. The model, the way Bill has done E4th, there are all the definitions are divided into two groups: high-level definitions and machine code definitions, the ones that you have to specifically target to the processor that you're running on. And the goal with E4th was to minimize those so that you could port it as quickly as possible. And what we have in the package that's now in here, where is it? This is the E4th subdirectory. E4th is stuck in here under VentureForth as an E4 distribution folder that's a sibling to the projects folder when you run it. And it's got E4th running from ColorForth, E4th documentation, the terminal program that is another SwiftForth program that's being a little bit more than a dumb terminal at the other end, the code words for VentureForth, and the high-level, the source words to recompile the whole E4th system is what is in this distribution folder for E4th. And E4th itself, the code words have to be written in either VentureForth or ColorForth or C18, what I think we're calling it C18, the ColorForth targeted to the chip. And just like a regular processor, you have a processor, and outside of that you have memory, and all of the high-level definitions go into that memory. And what we've got is an SD-RAM sitting outside the chip that's on the S40 board now, so that it's there, and when you get an S40 system, you can be up and immediately running an ANSI 4th using this E4th environment. It takes just 2 nodes on the chip to run E4th. And in the S40, they're the node 11 and node 12. Node 11 is the BITSI, the bit-threaded code interpreter, and a whole bunch of code words that use the return stack and so on. And then the stack and memory controller that has most of the arithmetic words in it. The bit-threaded code has a pretty unique thing. It's bit-threaded. It uses 1 bit of the execution token to differentiate between list words, colon definitions, high-level words, and code words. And in this implementation, because we've got 2 of these nodes, we broke the code words up into 2 different classes, code.r for return stack words and code.s for data stack words. The BITSI controller sits here, and on its internal stack, on node 11 stack, it maintains the instruction pointer and the return stack pointer. Node 12 on its stack maintains the data stack pointer and the top two items off of the data stack are cached internally in the chip. The list tokens are just an address in external memory with the high order bit set. We have 18 bits of memory addressable and 256K words. And so the top 128K words are being treated as the processor's RAM. We'll talk about the other 128K later, but the 128K that is starting at 20,000 hex is the external memory. And if the token has the high order bit set, it's an address into that memory space, and it's a list token. So you've got a list of execution tokens. If a token starts with 0, it's code. If it starts with 00, it is an address within the node 11. It's code.r, and it's just an address. These X bits don't matter, and it's got a 10-bit address for inside the node. The code.s tokens are cunningly encoded into the top 5 bits is a call instruction. They're not useful as address bits, but they are a call instruction. And the BITSy controller, when it sees that it's got a 0, 1, it just throws that whole execution token, it stores it in the port to the neighbor. Node 12 is a slave over here, the stack pointer. When it finishes what it's been told to do, it goes back and it fetches the next instruction from its neighbor port, and it just sleeps there, sits there drawing no power until node 11 has an execution token for it to execute. At that point, this thing is over here, and it calls to this address, which is an address inside the port, inside the node. This is basically the hierarchy, and then the matching it up for the code. I'm not going to go down through the code. There's enough other stuff to do. But wanting to just talk about it from the top. So this guy is sitting there in a control loop. It's sort of, the code here is not occupying code space out in memory. The machine code words are what you can fit into these two nodes. Now it turns out that isn't limited to the 64 words. You have, in both of these nodes, you have an up and a down port that are free, that are addresses within that node's address space, so that eForth can call those addresses. When it calls those nodes, it goes, the eForth controller goes to sleep waiting for the neighbor to do whatever it's been programmed to do. Now, eForth, when it comes out of the box, has a way of accessing all 4 of those neighbors. The down port, the down neighbor here has been default to what I call nada, just a word that sends a return back. It doesn't do anything at all, but it's there to verify that, oh, we can do something, that neighbor is alive and you're talking to it. Node 13 over here, let's see, 11 and 12 are the BITSy thing. 10 is the serial controller that Charlie just talked about. I have the same 4 words in node 11, xfetch, or fetch and store, and fetch IO and store IO that talk to the serial and set up its baud rate. Over on the other side, we've got 4 words that talk to the SDRAM. This node 13 is the user interface to the SDRAM driver. And in the 40, there are 4 rows of 10, so underneath node 13 is node 3 down here. Next to it is 14, and underneath that is node 4, and next to that is node 5. 3, 4, and 5, now those 3 nodes cooperate and talk to external memory or 2 parallel ports or whatever. Nodes 3 and 5 each have an 18-bit parallel bus. And node 4 in between them has 4 control bits and can also, by internal wiring, wake up the neighbor. If node 3, for example, goes to sleep waiting for the RAM to provide data, it's reading on node 3's up port, which is pointing down in this picture. Don't get confused by it. So it goes to sleep waiting for the RAM way out here to provide data on that port. Node 4 is doing all the clocking to the RAM. I believe that this is the only totally software-driven SDRAM controller. The controller is only being done in software. The clock, the whole, the biphase clock and clock bar are both being driven in software. So node 4 knows when the data is going to be ready. And at the appropriate time, it wakes up node 3 and says, time to take your data now, it's there. And it does the same thing on writing. But for writing, you put data out to the port, and node 4 tells you when the SDRAM has gotten it, and you can go on and write the next thing to the port. So to talk to the SDRAM, to talk to serial, it took 1 node. Talking to the SDRAM, it takes 5 nodes, because we have to cover 3, 4, and 5. Node 5 is doing the address bus, which has some SDRAM control bits on it. Node 4 has got the clock and other control bits, and node 3 has got the data bus connected to it. In order to get to node 5 and to node 4, I either have to go through node 3 down here, or I can go through node 14. Turns out there's a lot of stuff to do to talk to this thing, so going through node 3 is not appropriate. We want data to go through there as fast as possible. So we're talking through node 14. Node 13 and the SDRAM driver translates from our linear address to a row column address for the dynamic RAM. Node 14 over here is keeping track of the clock cycles and refreshes and doing all of that stuff. Node 4 is sending the commands out. Node 3 is reading the data, writing the data, and node 5 is putting out the stuff to memory. Now node 5 has 3 words of its 64-word memory occupied. That's all that it needs. Node 4 is almost full, probably 40, 50 words. Node 3 has about 10 words in it. Node 13 and 14 are both pretty full because they're doing administrative functions. But the ones that are actually talking to the outside world are pretty damn small because they have to be fast. And there's not much you can do in there. Studying that code, the SDRAM stuff here is a project, and it has a standalone demo thing associated with it, just like Serial and IDB do. So you can get in there and see and look at that code and figure out how it's doing. E4, sitting over here, just accesses. It accesses the IDB, SDRAM, and Serial projects to pull them in. So that E4 really only has in it these 2 nodes of C18 code, of S40 code. Okay. What I would like to quickly show is getting E4 up and the interactive debugger, which I think we'll probably we might end up calling a cooperative debugger instead, because as Charlie showed, you have to have the system that's under test, that you're debugging, has to cooperate in order for the debugger wires to get in and be able to be attached. Currently, I'm using one of what we call our test boards, a rather large monolithic thing rather than the small individual function boards that are going out. I'm just doing that because it's what I've been working on, and it's easier to make everything work there. For this one, I need 2 connections. I have to plug in a the serial terminal, and I have to plug in the board itself. Let's see, I've got it backwards. And I've got some, in my Windows environment, I've got some icons on the top over here that if I start up the terminal, and I'm going to move that out of the way because the other one's going to come in at the same place. Put it up a little bit. And this is the E4 terminal program that Bill wrote. Lets you use the function keys to do a whole bunch of, let's see, Control and then Shift F1. Whoops. Type. I'm not in the terminal yet. Still in Swift4. Now I'm in the terminal, and I can hit F1, Control F1, and Shift F1 to get, and if I had more space on the screen, you could see it going all the way over to F12. The keys that are available for changing various features, the triggering request to send data terminal, changing the spacing character, number of lines, the baud rate, and the COM port, and to upload files and such. One of the demos that we've got there, first I'm going to download F9, come. The library, and okay. Oh, I know why. I have not started up E4 yet, so it's a little hard to make it run. So I'll do that in this other window. Click the same one. That doesn't help. How about load E4? So it's going through this process of loading it up. Right now it's copying E4 out to the SD-RAM. The 5K words is all that E4 has in terms of its image. And it comes up in the interactive debugger, as Charlie showed, with the path and the stack of node 23. 23 is the one that sits right above 13. The SD-RAM has two independent users that can go into RAM without interfering with each other. Oh, the RAM is 32 megawords in size. We have a linear address space of 256K. We've taken 128 of that as our direct memory. The other 128K is paged access into that 32 meg. So there are 128 pages, no, 30, count them up. 32 meg times 464 is 128 pages of 128K words accessible in the bottom 128K of the E4 space. Each user, node 23 and node 13, or node 12, each user has their own page register, so they can make independent accesses to memory. So you can have DMA, you can do all kinds of stuff with this SD-RAM controller. The SD-RAM controller is built for random accesses. It is not fast because SD-RAM, when you're making random accesses to it, is not fast. This thing could stream data. If we had a streaming code written for it, it can stream as fast as we can move data across the chip. It doesn't have to go any faster than that, so we're comfortable with where it is. And so that's sitting now in node 23 up above there. Now I should be able to go over here, and if I can see which one. Yes. Thanks, George.
Well, it's, I just wonder the role of eForce with regard to this chip. Is that the standard for this
Is what? eForth is not distributed, nor is it supported by Intellisys. Bill and I will be doing that. But it is available for use with this, yes. It is, I believe, do we call it just public domain? I'm not sure what we say it is, but it's out there for use.
So it's not a requirement to use this chip?
Absolutely not. No, eForth is an application that runs on the chip that may be useful for your application. That's all. Okay, now I've got eForth up and running. What I had to do was hit the space bar when it comes up, same as the interface with Charlie, so that it does an autobot and makes sure it's running stuff. And then eForth, this is the high-level code from July. The last time we modified it was July, and the lower stuff was in September. And at this point, I should be able to do an F9 and get my lib demo. Come on, double click. All right. And then bring in the random demo. Now, it doesn't, eForth doesn't know what processor it's running on.
Yes.
Right? And so it's got machine code down there that execute code words, executes high level. It's ANSI forth up there. It doesn't know. And what I was just doing here, what this was doing was downloading source code files. These are the demo library and the terminal test demo are source code files that it just downloaded over the terminal to bring into eForth, and then typing the word demo. This is a little thing that puts out random character, random position, random color, keeps track of how many it's going. So it just, yeah, how many monkeys? It's just a thing to show that the machine is running. Now, while that's running, because we have two independent accesses to memory, I can go over here to the other one, and I'm in node 23. 23 has some user words to access memory, and one of those is to take an address and display 8 values from that address.
When you did that, you slowed down the right-hand screen.
It slowed a little bit, noticeably.
That's Windows doing that.
Oh, when I moved over there,
Yes.
that's Windows. I don't have the focus in this window anymore. I'm over there. And I think partly what you'll also find is that this one, when the focus is here, you're seeing the cursor bar. I'm not sure whether the numbers actually whether it slows down.
Yeah,
It does slow down a little bit.
Windows is putting greater task priority
On the focus.
So
Right. So it's not updating this. We don't actually know how fast it's really running, but the updating that we're seeing is going slower. But I can run this stuff, run the debugger over there. And that's what it just did. That's what there is code over here. This word FFX, fourth word is FX is easier to type than fetchx for external memory, and FF, there are multiple ones. So it just went and got and displayed 8 words at location 0. It's sharing the memory with eForth, and it turns out it doesn't really cost a heck of a lot. Okay, well, I'm going to show the debugger part now. And so to do that, I want to show how they're working together. That in order to get into node 12, to have the debugger come into node 12, it's creating wires across the chip for the path that it takes. So I have to create a path that's not going to destroy nodes 13, 14, and 12 in order to get there from node 19. So I've got to create a new path to do that. And the other piece that I want to do is to do something that you can see the effect of in eForth. So on 12, it's got the top 2 values of the stack cached. So I'm going to put some values there. And then I'm going to call this word that I've made that accesses the up neighbor, the stack node up neighbor. I'm going to call that one, and then I'm going to put a .s to display the stack. Well, what's going to happen? eForth is going to go there to execute stack up, and it's going to wait until the up neighbor releases, comes back, before it goes on and can do the .s. So when I hit enter, don't see anything happen. It's just hanging there. Now I'm going to go over here, and in this window, I'll make it a little bit taller so we can get more on the screen. What I want to do is create a path that's going from node 19 over to node 12 without stepping on anything else. So I'm going to create an IDB path, and I'm going to start. Excuse me? How about if I spell it correctly? Thank you.
You don't have to spell it correctly, just consistently.
No. In this area, I have to spell it correctly. I'm going to start in 19 and go to 18 and then to 28 and then to 27. Whoop. I need a comma. 28, 27. I have a period, don't I? That does appear to be a period. I have reading glasses and long distance glasses, and I need one for that and one, and I'm doing great. 26. It's a cinch getting old. Much nicer than getting dead. 23, 22, and now 12.
22 space.
Thank you. I'll go back and get that. Back to the end, 12. And then we finish the path thing up by doing that. And now I'm going to, since I'm coming in to 18, this is what is in the red stuff here. Path 1 goes to 18, so I'm going to assign IDP path to store 1 PA. Puts it into one path dot P And now it's still in going there. Now I want to, on path 1 to 12, hook. And if I do a dot S now, there are the top 2 values of eForce data stack are cached in node 12 on the top of its stack, and there they are. What's just below it is the stack pointer. So that's the address in external memory where the stack is continued. I can, and when I leave this, I'd better leave the 3 things on the stack the way that eForth expects them. But let's mess with them a little bit. Let's, well, Charlie said you can add them together, and then I'll dupe it. But then, let's see, if I say, these are some incantations that may get taken care of later. Just have to make sure I'm in the right node. And then 064.adrs to disassemble the code that's in there. And they all do various things. I want to find something that, that's benign, that works with it. _2 star. And that's at address 38. Again, because of some wordless things that I haven't worked out, I don't have direct access, but I do have that access. So it's an address 38, and I can say, let's do a .s again to remind me what's there, and then I can say 38 rcall, and another .s to show what it is. And I did it 2 times. Now I've got 14 on the stack over here. Now let's bail out. So what I do, I go back to, I'll go back to 23. No, I have to go back to 22. That gets me, steps me out of node 12, so I'm not interfering with eForth anymore. And now I have to tell eForth that I'm done. So I send it a return instruction, and that's something you learn pretty quickly, is that number. And I'm going to send it to my up port just with a store. So that I can take stuff off of, this is off of the host stack. These are numbers that are on the host stack. And in the target, in the debugger, fetch and store directly move stuff from the host stack into the target machine. And so when I release this is going to say to eForth that we're done. Go for it. And so when I hit that, it's completed the .s, and now there's 7 and 14 on the stack, and we're done. Cooperative debugging. That's it. Questions? You're setting up.
Where was this when I needed it last night?
It won't run on your 4th drive. Other questions? Okay, then Jeff, you ready to get into this?
How did you know the path? You set up the path.
It's 0 to 9, 10 to 18, and I knew where I wanted to go, and I've done it a number of times, and so memorized. Yeah, that's as good as anything, John. Yep.
This one is long enough. I mean,
Yes. Oh, yeah, it's plenty.
Okay.
Plenty long.
Great, then I